Okay, so for the first talk this afternoon, it is Javier Aramayona who will be talking about the first integral cohomology of pure mapping vectors.
Thanks very much. Thanks for the invitation. For putting me first here. So everything I'm going to say is joint work with Priyam Patel and Vlamis. So, all right. So I'm not a big fan of saying the main goal of the topic, but let me start by saying what the main goal is. So I'm going to describe, so very much like Castra, I have collaborators who insist that the mapping class group be called map. So, but who cares? So I'm going to describe the first cohomology group of the pure mapping class group with integer coefficients. So this is just homomorphisms from P mod to Z for all surfaces. So part of this is classic, and I'll explain the classic part. So for all surfaces means in particular for of finite and also infinite topological type. So depending on whether pi 1 is finitely generated or not. So I'll start by explaining this part, which is classic, and then I'll explain what we've done, which is this part here. So what is the upshot of this? What's going to happen is that, so if S has finite type, then in general, this is not true for all surfaces, but with some exceptions, some low genus cases, H1 tends to be trivial. But actually, when S is allowed to have infinite genus, then that's no longer the case. So if S has infinite type, then in general, this is not zero, and we're going to describe exactly how it's not zero. What a sentence. Can you, can you stop the camera? So what's going to happen is that H1 will be very much related to the structure of the space events of the surface. It's related, and we'll say exactly how related to the structure of the space events of the surface. So, okay. Let me say something concrete. What?
So in general is for both the
yeah, in general it's for both. So there's some exceptions, but then, yeah. And I'll say exactly how and when. So first, the more classic world of finite type surfaces. So throughout, I'll assume that surfaces are connected and orientable, and I'll also assume that they have no boundary. So I can write S as SGN. So G is the genus, N is the number of punctures, all marked points on the surface, and I'll feel free to switch between both. So 0 less than G and less than infinity. Okay. And I'm interested in the pure mapping class group. So the subgroup of the mapping class group whose elements fix every puncture point, pure mapping class group. Okay. And what do I say? Okay, so here's the theorem of, actually, what I'm going to, so Powell, so this is a well-known theorem of Powell, building up on work by John Berman and Mumford. Not only the first cohomology group is trivial, but first homology group is trivial. So if the genus of the surface is at least 3, then H1 P mod S is 3. So P mod S is a perfect group. And I would like to explain the proof of this because it's very easy and instructive. One gets to draw a picture that's a little bit drawn, but it doesn't matter. Okay, so what's the point of this? So what is the proof of this? So what is the proof? Oh, so yeah. So let's see. The first point is that P mod S is generated by plane twists about non-separating groups. Okay, that's, I don't know who put that. Really? Mumford. Okay.
Oh,
So there's a theorem of Mumford and licorice. And the second point is that any two such plane twists are conjugate. Yeah, because this is just because this classification of surfaces. This is just because of this little fact. Right? So when you take the abelianization map, these two facts together tell you that the homology of the pure mapping class group is cyclic. Right? Generated, so 1 plus 2, say that H1 is cyclic, generated by, say, some A, let's say. And the point is, what Kasra drew, the lambda relation. So this is on a sphere with 4 boundary components where you define the mapping class group to fix the boundary pointwise. So mod S surface of genus 0 with 4 boundary components and you like that. And then this is called A, this is called B, this is called C, this is called D. And then we have 3 other curves. Maybe this is called X. I'll probably get the labeling wrong, but this is Y and this is Z. Did I get it right?
You didn't tell us which way you're twisting, so it doesn't matter.
Oh, yeah, that's right. Yeah. Okay, so let's keep it that way. It says okay. So for some choice of right or left. And so what is the point? The point is that if the genus is at least 3, then so finally, if the genus is at least 3, then I can realize this picture using only non-separating curves. Okay, so I don't know if I can draw this. Let me see. So here's a sphere with 4 boundary components, and then you do this, and then this. And here you put 27 genera if you want, and some mark points. And then, oh god, I can't see anything anymore. So here's one of the curves, here's another one of the curves, and then the other one separates the two punctures that they're all non-separated. So I'm not drawing one of them. And so the point, okay, so the point of this is that A4 equals A2. And, okay. So, but in low genus, things don't work like this. So low genus cases, so in genus 0, it really doesn't work. So there's, actually you could do what Castro did. So Castro constructed a homomorphism. The mapping class group of, the pure mapping class group of a sphere with 5 punctures. So in this case, it says that, let me see. It's valid for all genera. You know. So when n equals 3, this group is trivial. So P mod SO4 is a free group on 2 generators. So this tells you that, so this, yeah, not write everything. If n is at least 4, then P mod SGN subjects onto a free group. Okay? Right. So it really doesn't work. If the genus is 1, then it turns out that the first homology group is Z mod 12. And I think this is just the fact that for n equals 1, this is PSL2. So I'm not sure how to put that. For all n. Okay, so it's not trivial, but it's finite, so maybe not that terrible, but a good point. So, I mean, this is kind of cheating, right? Because this is really using relations in the mapping class. So, I guess the point here is that if you allow to go to a finite index subgroup, then the same thing will happen. And the reason is that if you take a torus with yeah, okay, a torus with one mapping component, with one puncture. Then there is this hyperelliptic involution, which is central in the mapping class group. So the quotient is morally a sphere with 4 punctures. That's not very morally a sphere with 4 punctures. So you can play the same game. I mean, okay, so you don't map onto the pure mapping class group, but up to finite index you do, and then so the fact is that for all n, so P mod S1n virtually subjects onto the free group onto generators. And then if the genus is 2, then the same thing happens. So I think it was Mumford who proved that H1 is Z mod 10. But then, you know, same thing. So there's this hyperelliptic involution, which is again central, and then the quotient is 1, 2, 3, 4, 5, 6. 6 function sphere, and then the same thing happens. So P mod S to N virtually surjects onto the FT. Right? So I guess the real question is whether mapping class groups virtually surject onto Z. But yeah, that's a lot higher. Okay, so that's the classic world of finite type surfaces. Now I'm going to talk about infinite type surfaces. Right. Let me see. So. So again, surfaces are assumed to be connected, orientable. They have no boundary. And now pi1 of S is not finitely generated.
What if you took like an infinite tree in the plane and a regular neighbor to that?
Yeah.
Open regular neighbor, that should go pi1, right?
Yeah. No.
A tree in the plane?
It's like this.
Right, yeah. No, but no, but it's got infinity. Oh, you're right. Okay, yeah. I was thinking this other.
Okay, so how do you think about these surfaces? So before I wrote, so that equality of S with SGN, how you can classify surfaces up to homeomorphism. So here, there's also a classification of surfaces up to homeomorphism that may not be that familiar, but so I'll describe it in a second. So for instance, you know, concrete examples that you should be thinking about, for instance, a surface of infinite genus drawn that way, or a surface of infinite genus drawn this way. So the two things are not homomorphic because this has one end and this has two ends. And then, you know, there are many ways of, you know, I mean, okay, so you could take a torus with 3 boundary components, and then, you know, using a tree-like pattern, you know, construct a surface of infinite genus like that, and the space of ends here is going to be a counter set. You could do, you know, you could take SG minus a counter set. So, for instance, for G equals 0, it corresponds to erasing the genus here, right? So that's what we and then, so the classification of surfaces tells you that, no, there's something else I didn't say. So the space of ends here is a counter set, and the space of ends here is a counter set. But the two things shouldn't be homomorphic because, so here, every end are accumulated by genus. Meaning that every neighborhood of the end has a positive genus. Actually, infinite is positive genus. So there's the end. So there's the space of ends, and then there's the subspace of those ends that are accumulated by genus. Okay, so this is and then there's a theorem. So this is due to So in French, there's the problem of remembering
I
how.
think it even has the first one.
What?
I think it even has the first one.
That's even better. So there's no need to remember it.
Yeah.
Everything has an accent. So the homomorphism type of S is determined by the triple the genus of the surface, the space of ends, and the subspace of ends accumulated by genus. I'm not saying exactly how it's determined, but it's determined by that triple. And then, so the space of infinite-type surfaces is actually pretty big. So there's, yeah, so I don't know. So realization theorem by Ian Richards, I think it is. So these are subsets of a counter set. So that's the first part of the theorem, and then well, I guess. And then the second part is that for any two subsets of a counter set that you may choose, they are the space of ends and space of ends accumulated by genus of some infinite type surface. Okay, so every.
Sorry, n sub s is the number invariant
Topological
space.
space.
Oh.
It's the S space, okay.
Yeah, it's a topological space. As a topological space. Yeah.
And for that, do you care about how they accumulate ends and beds or just a homomorphism type?
Say that again?
For that, when you say it's determined by that data, do you care about how n
Yeah.
infinity embeds?
Yeah.
Okay.
Every pair, AB. So these are subsets of a counter set with B contained in A is the space is realized as the space of ends of some surface. So this is extremely lazy, but I mean, but hopefully it's clear. If not, we can ask. Maybe I'll be able to guide you. So, okay. So once you have a surface, then you can talk about its mapping class group. So maybe I should define the mapping class group of an infinite type surface. It's the same definition. Okay. So there's mod S. Is the mapping class group, homomorphisms up to homotopy. But now, this is a strange beast. So, so what topology you put on it? So you put the compact open topology on it, and then it's pretty big. And then, again, this induces every element of the mapping class group induces a homomorphism of the space of ends, and then you take the pure mapping class group. So it's the elements fix everywhere. And you put, a topology that comes for genus of group. And then, you may wonder what kind of a beast is this. And you'd be right to do so. But it has some structure. It's I mean, apart from being the same definition, which kind of gives you some perhaps false sense of security, safety, it has some nice features too. So let's see. So it's a theorem of my two co-authors, previous theorem of them. So theorem, so Patel, Vlamis from last year, which says that if the surface has at most one end accumulated by genus, then the mapping class group, the pure mapping class group, is topologically generated by Bain twists. So our way of saying that is that, so you can take, so this is the mapping class group with compact support, so this is a group generated by twists, so this is the closure.
I have a question. What topology are you putting on the mapping class?
The compact open, so the quotient of the compact open topology.
So I take that.
Yeah,
Okay.
yeah. So, I mean, yeah, pretty big, pretty wide. And then, otherwise, this is not true, but it's almost true. So, for instance, you know, if you have a surface like this, two-ended surface like this, so there's an obvious element of the pure mapping class group that you won't be able to get like this, which is a homomorphism that shifts a handle by one. Those are called handle shifts. If not, so otherwise, the pure mapping class group is generated by twists and handle shifts. It's topologically generated by twists plus handle shifts. Okay, so that's actually, I mean, it's good for getting a hand of what this group means, but actually we're not going to. Yeah, I mean, it's going to be enlightening in some way, but we're not going to use it. So the theorem that is really, really useful for us.
I have a question. When you're talking about the H upper one, is there any sort of continuity on your maths Z?
You're 10 minutes ahead.
Okay.
2 minutes. Okay, so the theorem that's really important to us is a theorem of so two independent, almost simultaneous proofs. So a Mexican team by Jesus Hernandez and Morales and Valdez, and then Bavard and Spencer, and Kasha. I don't know why minus. From last year. So the theorem is Ivanov's theorem on the rigidity of the curve complex. So the automorphism group of the curve complex, so same definition of the curve complex. The only thing is now the curve complex has diameter 2, but who cares? In general, yeah. So we have diameter 2. This is isomorphic to the extended mapping class group. Okay. So why do we care about this? Apart from its interest in itself. Is because this actually gives some structure on the mapping class group that we're going to use. So there's a theorem, or maybe there's a general philosophy that whenever you have a group that acts is the automorphism group of a graph with a countable vertex set, then the group is Polish.
So the left-hand side is some sort of topological group. It's not. So how do you see the topology on that?
Yeah, that's 2 minutes ahead. So there's a natural topology that comes from being the automorphism group of graph with a countable vertex set. So you choose an enumeration of your vertex set, and then you say that two things are very close if they agree on many, many curves. So that in principle is not the compact open topology, but there's the Alexander method, which these people proved for infinite-type surfaces, and that Alexander method tells you that the two topologies, which in principle were different, are actually the same one. Okay, so the corollary I care about this is that mod plus minus is Polish. So, yeah, Polish means that it's are separable, completely metrizable, so metrizable and then complete, and then it's a group, so the metric has to be invariant. The office action is Polish. And then any closed subgroup of a Polish space will be Polish. So this will tell us that, for instance, in particular, P mod is Polish. And why do we care about this? Because of what you said. I'll say it in a minute. And closed subgroups. Okay. So, oh yeah, okay. As I said, you know, there are two different topologies that end up being actually the same. So let me, maybe this is part 3, and this is, I'm going to actually construct and describe how to construct every homomorphism from the pure mapping class group to Z. Constructing homomorphisms. From P mod yes, to Z. So it's very instructive to learn how not to construct a homomorphism. So where is it going to fail? So this is just I'm going to assume, just because the notation is easier, that the surface has no puncture. So a puncture is a planar end. Okay? So I'm going to assume that every end of my surface is accumulated by genus, just because it's easier to write things. Okay? So every end is accumulated by genus, and this means in particular that the surface has infinite genus. Okay? So fact 1 is that if you take the subgroup generated by twists, this is the direct limit of mapping class group of compact surfaces. So you can take an exhaustion of your surface by your compact surfaces, and this group is the direct limit of the mapping class groups of those subsurfaces. So it's a direct limit of perfect groups. So trivial abelianization, and so this group is perfect. Okay, and this is, and now comes the fact that you were talking about, fact 2. So Polish groups are amazing because there is a theorem of Dudley. So this is sometimes called, often called automatic continuity from the 60s. If you have a Polish group and a homomorphism from G to Z, so this is called phi. This implies that phi is continuous.
So is Z in the discrete topology?
No, it's.
No, it's Z is.
Oh yeah. So this fact here will tell you that P mod, when you take the closure, that, I mean, in principle you don't know anything about the abelianization, but you know that first every homomorphism to Z has to be trivial, which is, I find it quite amazing. So in particular, if I for a moment forget this assumption here, Patel Vlamis' theorem will tell you that many mapping class groups have trivial first cohomology. Okay? So again, from that theorem, sorry for breaking the law. So I hope for constructing homomorphisms to Z are Amanda shifts. Many homology. homomorphisms. So this is what we're going to do. So for each handle shift, we're going to construct a homomorphism to Z that picks it out.
So, sorry. So this, handle shift, what happened to handle shift for you?
Nothing yet.
So in that case, the n infinity is equal to the n, right?
Yes.
So
this is just this group. It's not a pure mapping class group. It's a subgroup. So this you shouldn't look. Yeah. So any if you want to construct a homomorphism to Z, then you should look elsewhere, and elsewhere is handle shifts. Okay. So and for each handle shift, eventually what we're going to do is we're going to construct a homomorphism that picks it up. So the theorem says the following. Actually, I'm going to tell you how every homomorphism to Z arises. So this is a statement, and then I'll explain the construction. Yes. So you're interested in this group. What we show is that this is naturally isomorphic, and I'll explain how. This is this is the homology of the surface, the subgroup of this generated by separating homology classes. Okay, so classes that can be realized by a separating curve. Okay. This is the definition, right? So this is the subgroup of H1 generated by separating classes. Okay? So let me spell out a corollary of this. I'll explain the construction behind this in a second. Let me point out what this means for surfaces. Yeah.
I have a question. So for finite-type surfaces, the right-hand side is still non-zero. So this must be, there's an assumption in this about the infinite type? Something?
Yeah, he's doing it with them. I think it's just doing it.
Okay.
Yes.
Oh, you're assuming this S is equal to
Yeah.
Oh, okay, that's part of the assumption.
Yeah.
Okay.
Yeah. If you don't want to assume that, then here you have to close every puncture.
Okay.
But I don't want to keep track of when I close, and I mean it's not important, but it's needed. The notation is needed. So in particular, this means that H1 is trivial if the surface has at most one end. It's Z to the n minus 1 if this is n. And it has infinite rank otherwise. Okay. And then also, this tells you that, okay, so this is just spelling that out. So this is related to something we were talking earlier. So in the world of finite-type surfaces, homomorphisms between mapping class groups are kind of restricted. And this theorem here tells you, for instance, that, well, maybe I shouldn't, I don't know, I'm not going to state anything, but so this gives you, for instance, well, this gives, sorry. Suppose that you have a surface with 7 ends, and then a surface with 6 ends. Okay, so then, yeah, this is terrible. I don't know. So what I mean is that and this is not the hypothesis really, but what I want to say is that there exist, even if this happens, there exist homomorphisms from pure mapping class group. I mean, in particular, there exists a homomorphism from a two-ended infinite-type surface to the mapping class group of the surface of genus 2. Non-trivial. Just factoring through Z. And for instance, an obvious question that I think it's kind of cool is that, every map from every homomorphism from the pure mapping class group of the surface with infinite genus surface with 7 ends to the same thing with 6 ends should factor through abelianization. That seems reasonable. I mean, okay, in the world of finite type surfaces, there's a forgetful map. It's not clear how you forget. The end is too big to forget. Okay. So let me explain. Maybe I don't go out. 10 minutes. I got a little bit carried away. Let me show you how the construction works. So first.
Before you go to proof, are you going to state things for the when you don't have any genus ends? Like what happens when you?
I think that's a combination.
The second thing is empty. And what happens?
Yeah, I'm not. Maybe we can talk about it later. One has to be careful with these low genus cases, so I don't want to. Yeah, you can give the complete picture.
But in the flute, for example.
What is a flute?
The flute is the one in the infinite function, genus 0. So
Yeah. So
you don't see.
I don't think so. Yeah, that's a good name. So I'm going to give you an element here, and I'm going to explain to you how to construct a homomorphism to Z. Right? But it's easier, and actually it's not loss of generality to give. So let V, or well, I give you one of these, but let's assume it's simple. If it's not simple, then later I'll extend the construction by linearity. But for the moment, let's assume that it's simple, because it's easy. And then this V gives you a partition so V. So here I think I called it mu, but then V, and then I get confused. So this partition is a space of ends. Yeah? So the ones to the left, the ones to the right, and any partition like this. So if I give you this partition, then this determines V up to sign. Okay, so okay, fine. And then we're going to choose. So maybe I should draw a picture. Here's a picture. So the surface continues like that, maybe. And then I'm going to choose once and for all some n, say V plus. So the n is here. Some n, and I'm going to fix it. And then the first thing I'm going to do, so step 1, I'm going to construct, so for each gamma, a representative of this homology class, we're going to construct a map, actually a non-trivial map, which is good, from the set of curves homologous to V. So it's a subgraph of a curved graph, but I don't care that it's a subgraph. It's just a set of curves to Z. Non-trivial. And so how do I do it? So let's see. Let's suppose I give you a curve here, C. So here's gamma. So let me see. Gamma is here. And let's suppose that I give you some C. And C doesn't need to be disjoint from gamma, but let's suppose that it is, because it's easier to see. This gives you the clue why the map is non-trivial. There exists some compact subsurface with every boundary component separating that contains these two curves, because curves are compact. So I choose some R, contained in S, with C, so here I'm going to write what it is, with C union gamma contained in R. And I implicitly assume that every boundary component of that subsurface is separated. And then I choose, given this choice of R, so this is R, there is only one boundary component that separates the end and the surface. Right? So I'll call it delta 0. Okay? So, and then, so let me not write it, okay? Because I'm almost out of time. So delta 0 is that boundary component. And then I said, I write GR of C is the genus of the boundary component of R minus C containing delta 0. So, 4. Okay, so the R minus C, and I look at the component containing delta 0, so that number is 4 here. So the number I put here is GRC minus GR. Okay? And obviously, from this picture, you can see that this map is non-trivial. Okay?
And
so
does this depend upon R as well?
No, but it does depend on gamma. And understanding exactly how it depends on gamma is the key. So, lemma, let me see. Suppose gamma and delta represent nu. So how there's the homomorphism associated, the map associated to gamma, and then the map associated to delta. So actually it turns out that the difference is constant, and it's a number given by phi gamma of delta. Okay? So now you get P mod. Actually, this P mod acts here, because it's determined by the partition of the space of n's, and this fixes the space of n's. So lemma 2, how does it act? How does a mapping class change this data? Then phi gamma composed with f minus phi gamma. This is phi gamma of f gamma. Okay. So this is just you write down the definition. This is a one-line proof. And so what is the map? The map is so I'm out of time. V goes to phi gamma of f minus phi gamma. So the claim, the proposition is that that this map gives you so this is too slow. So from V you cook up a homomorphism from P mod S to Z given by to each f. I associate this number here. And then you prove that it's a homomorphism and it's well defined. And if you have like, if here you put a handle shift, then the value you get, the homomorphism is non-trivial. So here's the handle shift like this. It's non-trivial exactly when the homology class cuts a handle shift and 0 otherwise. So, and then you work more, you extend it by linearity to all elements, and then you work some more and prove it's an isomorphism. And that's it. Thank you very much. Sorry for going on.
Other questions?
Can you say anything about H upper 2?
No, not me, but maybe. Yeah.
How do you know there's nothing else?
You prove it's an isomorphism.
How?
Actually, at some point, you prove that P mod S is a semi-direct product of this guy that you didn't care about, together with some group generated by handle shifts.
So with those, we have this partition into V plus and V minus. So I think you said something that it can be realized by curves. Can it always be done by a single simple curve, or would you need a multi-curve in general?
It's a simple curve. The statement is simple.
So it can always be done with one curve.
But I mean, this was part of the assumption.
So I was asking about things back. If I just give you a partition of the space of n, so can I just find a curve which actually does the partition?
If he's asking what is the definition of H
No, I know.
separating, is it like generated by simple
But
curves?
no, by separating.
Or separating multiple?
Yes, I don't think so. So you probably need multi-curves.
Okay, well, our next talk here is in less than 10 minutes at 2:40, so let's go ahead and thank Javi again.